particle-laden flows are a very specific category of multi-phase flows. In particular, particle-laden flows are a subset of dispersed two-phase flows, which in turn are a subset of two-phase flows, which in turn are a subset of multi-phase flows. Let's take a more detailed look to these categories. Multi-phase flows are flows of materials with either different states or phases, that is, gas, liquid, or solid, or with different chemical properties but in the same state, such as liquid-liquid flows. For instance, we can have a three-phase flow in which gas bubbles are entrained in oil droplets and flow over a water base. Two-phase flows are a subset of multi-phase flows in which only two materials are involved. These include, for instance, stratified flows of oil in water and liquid vapor flows with phase transition. In dispersed two-phase flows, one phase is not materially connected. Dispersed flows are mixtures of a primary carrier fluid and a secondary dispersed phase, which is in the form of either gas bubbles, liquid droplets, or solid particles. For instance, we can have dispersed flows of gas bubbles in a liquid, dispersed flows of liquid droplets in another liquid or a gas, or dispersed flows of solids in a liquid or a gas. In the last case, we talk about particle-laden flows. The physics and modeling of particle-laden flows will be the subject of this course, and it will be described from an engineering perspective. Case studies provided by academic and industrial partners will be illustrated, referring to several application examples. These include, among others, oil and gas extraction processes in fields with sand production, hydrotransport system in the mining industry, sediment-laden flows in hydraulic machines, and particle erosion of concrete hydraulic structures. One of the key parameters characterizing particle-laden flows is the volume fraction or volumetric concentration. Let us consider a volume containing the fluid and a certain number of solid particles, which will be assumed to be monodispersed. That means all identical to each other. The volume fraction of the particle phase is defined as the volume occupied by all particles divided by the total volume of mixture. So, if we have NP particles with volume Wp, and we call the total volume of mixture W, then the volume fraction of the particle phase, called alpha p, is given by Np times Wp divided by W. The volume fraction of the fluid alpha f is the volume occupied by the fluid divided by the total volume of mixture. If the volume fraction of the fluid is written as W minus Np times Wp, then it immediately follows that alpha f is equal to 1 minus alpha p. The density of the mixture, ρm, is another important parameter. Let us again consider the same sampling volume with monodispersed particles. The density of the mixture is defined as the total mass of the mixture divided by the total volume of the mixture. If we introduce the density of the fluid ρf, that is, the mass of the fluid divided by the volume of the fluid, and the density of the particles ρp, that is, the mass of a particle divided by its volume, then the density of the mixture is equal to the volume fraction of the particles times the density of the particles, plus the volume fraction of the fluid times the density of the fluid. Finally, let's focus on the case of polydispersed particles, that is, the case of particles that are not all identical to each other. In this case, it is convenient to group the particles in n classes in such a way that all particles belonging to a certain class are characterized by the same geometry and material properties. For instance, we might have three particle classes, A, B, and C. It's quite easy to extend the previous definitions to the case of n particle classes. In fact, the volume fraction of particle class J is defined as the volume occupied by all particles of class J divided by the total mixture sampling volume. It can be demonstrated that the volume fraction of the fluid plus the volume fraction of the n particle classes is equal to 1. Finally, the mixture density is given by the density of the fluid times the volume fraction of the fluid, plus the sum over the n classes of the product between density and volume fraction of the current class.